day, so make sure to get those in. There is a late penalty, if you're turning it in later. The other thing is I will be gone next week. Oh yeah, sorry, go ahead.
End of the day as in end of class or end of the day as in end of
Midnight. Yeah, 11:59. Don't actually try to turn it in at midnight. Yes, so yeah, make sure to get that in. Yeah, so then I'm traveling for a conference next week, so I'm leaving actually on Wednesday. So that means two things. So my office hours, I won't be holding office hours this week. But if you want to schedule something, I can probably make it work. So just email me if you want to meet in lieu of our normal office hours. And secondly, next week's classes are going to be covered by Yanni, our TA in the back. She's giving the thumbs up. She's going to be great. Yeah, and so I'll remind everyone again on Wednesday, but do keep that in mind. Okay, any questions about any of that or concerns? Cool. So today we are going to start off hitting a subject that I think was brought up maybe last class or the class before that, which is outliers. So let's get into it. Outliers. So let me draw a plot here. X's and Y's. And so I think hopefully people have heard about an outlier before. So outlier analysis. So this is when we think about data points that differ statistically from other observations. Okay. So let's suppose we've got kind of this cluster of points down here. Maybe look something like this. And then we have a data point way up here. Okay, so you can imagine if we are drawing a best fit line, right? If it's a ordinary least squares regression, it's kind of a line that minimizes the distance from each point to our fit, right? And you can imagine that if there's a point all the way up there, it's kind of like pulling your line up a little bit. Okay, so raise your hand. Who thinks that this point out here is an outlier? Okay, cool. Most of the people. What about if the point was over here? Raise your hand if you still think that's an outlier. Okay? Most people, but I see a couple people put their hands down. Okay, what if I put it over here? What do you guys think? Raise your hand if you think it's an outlier. Wow, no one thinks that's an outlier. Interesting. Okay, and so, yeah, we see people have different opinions about what constitutes an outlier, right? And so, in the same way, kind of that I asked you guys about who thinks that this line or another line is the best fit line when we were drawing lines through all of our cloud of data points, right? I'm asking you guys what you think about what constitutes an outlier, and it's kind of the same thing, right? We're going with our gut, we're like, oh, that seems pretty far, that's an outlier, and then some people say the middle one, okay, that's like close enough that it's not an outlier. So same thing, we want to think about objective measures of what constitutes an outlier, right? We don't want to just use our gut and say, hey, that point looks really far away, or it seems like that point doesn't really fit our data, and so I'm just gonna consider that an outlier. So the first thing we're gonna do today is talk about like quantitative objective measures of determining whether something is an outlier, right? Which is not talking about what I'm gonna do with an outlier, we're just identifying them. And then we're gonna talk about what you might do if you encounter outliers in your analysis. Okay? So there's two kind of main ways that people will try and measure whether or not a point is an outlier. So the first of which is called leverage. So this is how much would predicted value change if observation were shifted 1 unit in y direction. Okay. So this is always between 0 and 1. Okay, so the equation for this looks something like this. KII is equal to change in delta y hat divided by delta y. Okay, so let us think about what this means. So in a plot that looks like this, I may have a best fit line. Okay, that's not a very good best fit line, like that. And if I were to take a specific point, let's take this point right here, and I were to move it in one direction, up or down, what happens to the red line? Any ideas? Okay, if I move that point up by 1 unit, does the red line go down? Does it stay where it is? Or does the slope increase? Increase. Yes, that's right. So let's take this and I move it up. The red line will slightly move up. Okay. And so when I move this up by 1 unit, leverage is figuring out how much the predicted value for that particular point will change. So if the slope of the line slightly goes up, right, I have a new predicted point. And so if I do something like this, up by 1, which causes my line to, let's say my line slightly goes up like this. So this delta, you can zoom in, right? So that distance right here, the ratio between that distance and this distance is equal to my leverage. And so you can imagine if the point is farther away, like this one, if it's farther away from the line, and you move by 1 unit, does the slope change more drastically or less drastically? What do you guys think? So it'll actually be more, right? And the reason for that is actually having to do with the squared error term, right? So the farther away you are, the larger the error, because it's getting squared. So even though you have kind of like a 1 unit shift and a 1 unit shift, if you're shifting by that 1 unit away, farther away, then it's going to look like you have more leverage. Okay. Also, there's one other. I'm not going to say obvious, but there's one other kind of interesting phenomena that happens with specifically the leverage value. So if you think about the slope kind of increasing and decreasing, you are kind of like a what is that thing on the playground? The seesaw. It's like a seesaw, right? And so actually, if the slope were to increase, the chain right at the pivot point, it turns out that your prediction value doesn't change very much, like right there, right? Right? Even though the slope is moving up and down. Whereas you can imagine if I have an outlier that's like centrally located, the leverage is not going to be as large as if I have points that are kind of on the edge of my seesaw. Right? So things out here, away from the kind of median value of the data spread, will tend to have higher leverage values. Okay. So nice. Does that make sense to everyone? Okay, great. So that's leverage. Pretty straightforward. And this value is going to allow us to specifically compare the relative leverage of different points so that we can come up with an objective measure, if it's beyond some kind of threshold that, hey, I'm going to call this an outlier. Okay. The second way that people typically identify outliers is something called influence. And you may also hear this called a Cook's distance. It's the same thing. Okay. So Cook's distance is the effect of deleting the point. So distance I is equal to, so we'll write out the mathematical form of this, the sum of j over j of y j hat minus y j hat parentheses I, and I'll explain what that means in just a second, squared. Okay, so this is kind of like kind of looks similar to our error term in some ways, divided by k times our mean squared error. So k is the number of coefficients, and this guy here, this is our fit value without yi. Okay, so what is going on here? So the idea is I run a linear regression and I'm now able to make predictions for each point, right? Adjust the point that falls on the line corresponding to one of the data points. And then I run the regression again and I leave out the point that I wanted to figure out if that is an outlier. And by leaving that out, my line now shifts, and I can take the difference in these. And so what ends up happening is if the line shifts a lot when you drop the point, right, then you have a large influence. And if it doesn't, then you don't. Okay? So let me draw an example of this. So this might look something like x, y. Okay, let's do something like this. Okay, and then I'm going to have a point up here. So that's going to be, we'll call it our outlier point. And if we have a fit that goes through this, maybe that looks something like this. I don't know, I'm just guesstimating here. Okay, and so if we want to figure out the influence of this point, essentially what we do is we drop it. So let's get rid of that point. And now I'm going to draw a new fit line that might look something like this. Okay? And so that point used to be up here, and so I will have a prediction here and a prediction here, right? So this point here and this point here. So this is my yj hat, and this point is my yj parentheses I hat. And you can see if I take the difference of those two, right, so that's going to be this distance here, that will essentially give me something about the distance once I square it and divide by k times the MOC. Okay? So you can imagine that if I dropped one of these points down in the cluster, the line may not shift as much. Yes?
Can I just double checking, but that's y I hat and yj hat?
Yes. So this is hang on. Okay. This point is y. This is yi. Slash yj. They're kind of the same thing in this case. This is yj hat, which is the predicted value when I have that point in the regression line that I made. And this is yj parentheses I hat, which is the fit for the prediction line when I drop that point. Okay? Questions? Okay, so you can see, oh, yes.
So, seeing that both of these tests, we can test only one point at a time. Is that true?
Yes, if you were to do it manually, then you would be testing them one at a time. But luckily for us, you can say Cook's distance or whatever the algorithm is, and it'll just give you that value for all of the points in your data set. And then we can compare. So this is, yeah, it would be a little tedious to do this by hand and even to do it manually one at a time in the code, but the code will do this for you. This is kind of just background so you understand what the values are actually like doing and how they're generated. Yeah. Okay. Okay. Any other questions about this? All right. So we've got our two ways of doing this: leverage and influence. They are doing slightly different things. Leverage is if I move the point up and down, how much does my line change? And influence is if I take the point away, how much does your fit change? Okay. Similar, but not quite the same. You may find that most of the time they're going to agree, but some of the times, right, especially if you have like points in the median area, you might not have a lot of leverage, and so you would want an influence to check out if it is actually making a big difference. Okay. So let's go over to our studio and let's take an example, or let's look at an example of these guys. All right. So we are going to use our favorite old typical regression make-believe data set that I've been doing a few times now. And this is going to look pretty similar to what we have before. And let's just take a quick look. Okay. Hopefully familiar looking to you guys. We are generating a make-believe data set of x's and y's. We're adding some error into it, and then I'm plotting it, and we can see the spread of the data through my x's and my y's. There's like, we know that there's some relationship that exists, but then we've artificially added some noise. Okay, and what I want to do now is I would like to add a single outlier. So to my x, we'll do something like this, and to the y's, we'll do something like this. Okay, so I have combined my x and my y onto those vectors, a single data point at x 100, y is 20. And if I replot this, hopefully we can see the presence of that outlier. Okay? So you can see it's like way over there. So it looks like it doesn't belong. Okay? And let's see here. I'm going to put this into a data frame. Does anyone remember the variable name that I had for that data frame? It's like forModel.1, is that right? Okay. So x equals x, y equals y. Run this. If I double check this, we'll see, okay, I've got the random points, and then at the very end for the 101st, I have 120, that's my outlier. Great. So I will now run a regression. Y on x, data equals forModel.1. Run this thing. And actually, let's just take a look at what our model results are. We've run this enough times where hopefully you guys have some sense of what the model outputs are going to be. I think we had something like a slope between like 0.45 and 0.55. It was statistically significant, right? R squared value of like 0.67-ish. Okay, all that jazz. So let's see how that changes when we add one outlier into our data set artificially. Okay, great. So here, so the slope is still pretty statistically significant, but we are much farther departed away from our true value of 0.5. And actually, if you remember, even though a lot of the previous values weren't actually kind of right on the money, within a reasonable standard error, I think it was like less than 2 standard errors away, you were usually within the true value. Okay, adding this outlier has now changed that so that, how many standard errors are we away from our true value? Something like 2, almost 3. We'll say like 2.5 standard errors away, which means that the likelihood or the chance that the slope that our model is predicting is the same as what we know the true value to be is like very small. It's probably less than, 3 standard errors is like 99.7%. So this is probably, less than a 1% chance of being the right value. And we also notice our R squared has dropped pretty significantly. It's about 0.1 lower. So there's like a couple metrics here that we have some concern over, especially given kind of what we know about this regression specifically. Okay. So how do we calculate leverage and influence? So the first one, leverage example. So this is leverage hat. We do something like this. So hat is the way that it's like individually grabbing the prediction values. So I can do this, and I can plot that. And we can see what came out of our hat function. Okay. So leverage looks something like this. Like I said, your leverage values are always going to be between 0 and 1. And you want to look at the relative leverage of specific data points compared to other data points here. And so I guess with leverage, you are still making some kind of arbitrary call in terms of how different it needs to be, right? But compared to kind of eyeballing whether or not a distance is far enough away, this is at least standardized in terms of distances across any data set that you'd be doing, right? And so you could, for example, come up beforehand and say that if the leverage of a data point is greater than, let's say, 0.1 compared to leverage of other data points in your data set, then you can say, okay, let's treat that as an outlier, right? Whereas you wouldn't be able to make that kind of generalization on any arbitrary set of data because the distances are dependent on what's actually in the data, whereas with leverage it is not. Okay? I will say that I think leverage is, for that reason and for the reason of the greater leverage at like the edges of your data set, for those two reasons, I would consider leverage to be maybe a little bit less popular, a little bit less robust than using Cook's distance or influence as a measurement for outliers. But this is a handy way of doing a comparison, or at least verifying, for example, the influence of points. You can see that oftentimes if you have points that have a large Cook's distance or large influence, that they will typically have a correspondingly large leverage point. Okay?
Could you show us what you mean by like putting the outlier closer to the middle of the data set?
Yeah, sure. Let's just do this. So, hang on. Let me take a look at this again. Okay. So let's do x of 25, and we'll put y at some crazy number. We'll put y at like 60. Okay. So let me do this. 25 and 60. Okay, so if I were to run all of this again, so now I've artificially created something that's like kind of in the middle of the data set as opposed to like out here. And so this is the seesaw analogy, right? It's about how much the slope changes. And so if you're close to the pivot point of the seesaw, even if the slope changes a lot, the predicted value for this may not be really different. So I think this should give us a leverage value that's gonna be maybe not as big as the other one. Yeah. So you can in fact see that for all of the leverages there isn't one that like really sticks out. So in this case, right, when you have an outlier in the sort of median area, you will miss it in the leverage plot. Okay. So let me have that as a, yeah.
What was the value that showed you the difference? Is r squared, the one that changed to 0.1 or whatever?
Sorry, the which one?
So for, yeah, to decide once we know the distances
Uh-huh,
or the influence of each point,
the leverage.
the leverage.
I know, I always want to say influence, but influence is actually one of the terms, so we can't say influence. So the one that has the more leverage, yeah.
I guess two questions. What's a good logic to say I want to treat this as an outlier?
Yeah, okay, alright, so, you wanna see, so for leverage, right, we haven't gotten to influence yet, but for leverage, I plot all of the leverage, so this is, you know, for x1, the leverage is this, for x2, the leverage is this, and so on and so forth. And one of the points should be really different, essentially. And you can come up with some choice of a threshold for that. It's still kind of eyeballing it, but the idea is that it's a standardized eyeballing because you are not looking at things with vastly different distances. It's all like this one leverage value, right? So does that make sense? Like if I were, so for example, if I were dealing with a data set on housing prices, right, you might be operating in the hundreds of thousands or millions of dollars, and so distances is on an order that could be a lot larger than if I was looking at a data set on like hot dogs, right, which could be like a couple dollars in variation. And when you deal with leverage, the distances that you're talking about in comparison are always going to be like between 0 and 1. That's kind of the benefit of doing it with the leverage. Does that make sense to everyone?
With respect to the rest, we could
Yes.
decide if it's 50% more leverage than the others, or
Yes.
or twice the
Yeah,
leverage of the others.
you can come up with something beforehand.
You touch the point, if you know more about the data, then it makes sense what to tolerate.
Yes. So I'm just gonna add a note here. If the outlier were x equals 25 and y equals 60, then leverage wouldn't find it. Okay? And let me change this stuff back. Oh no, wait. I have to rerun all of it. There we go. Okay. So for influence / Cook's distance, for example, it's literally a function called Cook's distance. And you just put in the model, and it will give you all of those. Okay. Cook's distance is a little bit more standardized actually, and there are kind of threshold points that people say. Some people say, oh, at like above 0.5 it's an outlier, or above like 1 it's an outlier. So this is, yeah, maybe a little bit more standardized to use as long as it's above some kind of threshold, right? And you can look up what commonly used thresholds are, then we would consider that an outlier. Okay. So Cook's distance is, yeah, just very slightly easier to use. All right. Questions about how we identify an outlier. All right, so now that we've identified and found outliers in the data set, then what? What do we do? So here there isn't really necessarily like a strict statistical procedure of like what to do when you find an outlier. And in fact, there's a lot of disagreements about what you might want to do. And I personally am very much more in the camp of like, leave it in the data, right? And interpret your models as such with the recognition that there are things such as outliers that exist in the data. So I tend to think more that really the data, and maybe this is influenced by the type of analysis that I do and the data sets that I work with, right? But you know, outliers are an acknowledgement of the fact that you know, outliers do exist in the real world, and you know, it really is context dependent on what you're trying to do for whether or not you should keep them in your data set or drop them, right? And so what I will say is that think carefully about what you are trying to do in your analysis, about the conclusions that you're trying to draw from your analysis, whether it's going to be generalized to everyone or generalized to like a subset based on the fact that you've gotten rid of an outlier, right? And so my number one advice here is that, you know, definitely check your data set to see if you do have outliers or not. And, you know, if you are finding them using leverage or influence, don't just like blindly drop them. Like think about it first before you decide on a course of action, right? Because oftentimes I find that researchers will clean their data set, they will identify the outliers and they'll just drop them, and then they'll run their analysis without really thinking about the implications of doing that. Yeah.
I'm gonna help make your point. On energy systems, we learned that the UK was flying through the North Pole a lot and finding there was no ozone, no metrics for ozone, and they didn't want to look like fools, so they just thought it was a mistake. But after years, they said, "No, we need to bring it up to NASA," because NASA kept saying everything was fine, but they say, "Hey, y'all, there's no ozone."
Yeah.
And then NASA said, "Yeah, we treat them as outliers." So for years, maybe 3 years, NASA just said this is an error, this is our outliers, and finally UK scientists said, "No, we have, that's how they found the hole in the ozone layer."
Yeah. Yeah, see, even NASA gets it wrong, guys. Okay, so I am not saying to not drop outliers, but but you need to think carefully about what it means to actually drop data and the implications for your analysis, right? Which is maybe something that NASA should have done. I don't know that particular example, so I can't really speak to it, but yeah, you could be missing important things if you got rid of them. So I'll leave it at that and just say that outliers, dealing with outliers is more of an art form than kind of a science, right? We've given the objective, quantitative ability to now identify the outliers, but what you do from that point is kind of up to you. Yeah. Questions, comments, disagreements? All right. Back to notes. That's what I've got to say about outliers for today. And next up, we are going to talk about an extension of essentially what we've been doing so far. So, yeah, let's get into building up our foundation of linear regression. Actually, pretty much everything that we've done so far is known as univariate regression, which means we have one x that is regressing, or y being regressed on a single data variable. But actually, right, the generalization of this is known as multiple regression. So, multiple regression. So this is extension of simple univariate linear regression to predict the value of a variable based on the value of two or more other variables. Okay, so what does that mean? We are going from something like yi is equal to beta 0 plus beta 1 x1I plus epsilon, going to a generic, so yi equals beta 0 plus beta 1 x1I plus beta 2 x2I, and so on and so forth, up to beta n x n I plus epsilon I. So the top equation, hopefully we're all familiar with this at this point. It is a univariate regression with a single explanatory variable. I guess you could consider the intercept kind of an explanatory parameter. Down to here, where now we are dealing with a generic n number of explanatory variables. Okay. So, one explanatory variable, right? We've got our typical thing here, pretty straightforward. And you've got a line, you can do it with a different color, a line that looks like this. We're all familiar with this at this point. And I can continue to add in dimensions. And so maybe something that looks like this. So if I have two explanatory variables, so maybe my y is still here, my x1 looks like this, and then I might have x2 in like a 3D plot, right? So something like this. Okay, I'm always kind of bad at drawing these 3D plots, but I'm gonna draw points and just imagine the larger the points are, the like closer they are to you, right? It's kind of like a 3D perspective thing, so you might have something like this. Something like this. Okay, and you would end up with, instead of a line, right, you would end up with a plane in 3D. So something like this. Okay, so I'm hoping you guys can kind of visualize what this looks like, right? So you have points scattered in 3D space, and then you have a plane that cuts through those points. Very similar, right, analogous to how you have points in a 2D space and a line that cuts through these. And the betas for each of my variables, right, is actually the slope in the dimension that I'm looking at, right? And so the slope for x2, the beta for x2, is kind of the slope that I've drawn in this direction. It's, let's say if x2 is positive here and negative here, it's kind of going up, and so you have a positive slope. Whereas for x1, right, negatives that way, positive this way, and the slope is kind of like this, so maybe it's like slightly negative, okay? And as far as like visualization goes, that's like as pretty much, you're gonna get limited on going any farther than this, really, when we think about this fit analogy, right? So yeah, you can probably squeeze in a couple more dimensions if you're doing some kind of like color and maybe shading, yeah, but much more than that really is going to be very difficult to visualize. And so we need to think about the intuition that we've built through other metrics, right? So we've talked about things like standard errors and R squared, which is a piece of the puzzle. We know how to interpret those and what the implications of those, you know, in a univariate versus a multiple regression is actually not really that different. We talked about residuals, right? A residual plot is particularly nice, right? Because it looks at y hat versus residuals. And so even in a 3D plot, I have a distance of any of these points to my plane. That's a single residual value, and then with your y hat fit, it's still a 2D plot. So I could have 10 quadrillion variables, and I'd still actually be able to look at my, I'd still be able to look at my residual plot. Okay? Mean squared error, single value, residual squared error, single value, these are things that we can still leverage outside of your univariate regression. Okay? Any questions? So I have one word of warning here. We actually mentioned this in one of the lectures, but caution when I is approximately equal to n. What does that mean? Actually, let's just do this. We'll do a quick example. This has to do with the degrees of freedom thing that I discussed in a previous lecture. Degrees of freedom is kind of describing the flexibility of my fit to hit certain parameters, and you can run into some problems. If I have two explanatory variables and I have two data points like this, you want to draw a plane that can fit through these 2 points. How many possible planes fit through 2 points in 3D? Okay. Imagine if I had a piece of paper and I had a point in space here and a point in space here. How many ways could I orient that piece of paper to pass through 2 points in 3D space? Infinite, okay? So the analogy would be if I had x and y, and I had a single point here. How many lines can I draw to pass through this single point? An infinite number, okay? So, as this happens, as the number of data points approaches the number of parameters in your model, you lose your degrees of freedom, and actually you cannot run these models. So it would not work. The model would break, right? Because it cannot find a single line or plane or hyperplane or whatever that would, there would be an infinite number of solutions to that optimization. Okay?
So the more constraints and more parameters, the more likely you'll get a
Yes.
smaller series of solutions or
Yeah, really, it's, so I would, so as a generalization, yes, but the intuition, I would say, is about the relative number of data points and the relative number of parameters and how close they are to each other. Okay. Questions? All right, let's take a look at an example of a multivariate regression, or sorry, a multiple regression in R. Okay, so multiple variable regression. We are going to do, let's do 4 variables. And our x's are going to be randomly generated in the same way that we did before. I'm drawing from random and uniform distributions. There's going to be 100 data points. x1 It's gonna be between 0 and 50. X2 is gonna be between 0 and 100. Oops. X3 will be again between 0 and 50, and X4 is also gonna be between 0 and 100. Okay. And we're gonna have our error term, error dot multi, and that'll be kind of the same size. Okay. And the y is gonna be defined, so this is our true value of y, and we are going to define this as 0.5 times x1, same as before, but now we're gonna introduce 2 times x2 plus error dot multi. All right. So note in this case, y is a function of x1 and it is a function of x2, but it is not a function of x3 or x4. Okay? And if I were to plot this, so you can create windows to do multiple plots all at once that looks something like this. And I'm just gonna copy and paste this guy a couple times. And I'm gonna change these guys. Okay. And 1 second. Okay, so we define our y. Oh, I misspelled something. Oh, I didn't sign it. Okay. Run this. Okay, and if I run the plots, we look something like this. I'll pull this out. Okay. I know I'm probably blocking from some people, so we'll do this. Okay. So it is important to look at the data, right? And we kind of emphasized that in an earlier lecture. But when you get to multivariate stuff, you are now thinking about like combinations of influences. So when I view things kind of intuitively and I look at this data, okay, what do you guys think? Tell me about the relationship between my x's and my y. Yes.
Based on the graphs, there only really seems to be a relationship for x2.
Yeah, right. So to me, x1, x3, and x4 look to be fairly random. It is difficult for me to identify a sort of relationship between those x's and my y outcome. Whereas in x2, okay, it seems very clear, right? Like I can see this trend and my expectation, you know, if I had, if it was my only, you know, if I didn't have any preconceived notion about what y is defined as, maybe if I ran a regression across these 4 variables, I would hope to see that like x1, x3, x4 are not significant, and that x2 is going to give me like a clear slope, right? Does that make sense to everyone? Okay, so let's run the regression and see what happens. Example model 2, lm y dot multi, and this is going to get regressed against x1 plus x2 plus x3 plus x4. Okay. I run that. Summary example.model2. I run this and let's take a look. So let's keep in mind our true equation is 0.5 times x1 and 2 times x2. Visually, we have a hard time seeing what x1 does. How does our linear regression do? x1, about 0.55, very statistically significant. x2 is about 2, and very statistically significant. x3 and x4, they're both values that are kind of close to 0, and we say statistically we're not really confident that they are different from 0. Okay. So in fact, our multiple regression model that we ran, simple model, but it is able to really nail down the true values, right? And so it turns out that when you do have a true linear relationship between your x's and y's, you actually mathematically can't do any better than what a linear regression is telling you, right? You just need to count on the fact that you need to count and rely on the fact that the relationship is truly linear, which arguably, my little holder fell apart. All right, one second. Arguably not that many things in the world are going to be truly linear. Let me mute this while I put it on. Okay. Any questions? Yeah.
Can you scroll up just slightly on the
Sure.
actual script?
Up here, or in the console? In the console or the notepad?
The console.
Okay, up
Excuse
here.
me, the notepad.
Or the notebook.
The notepad, yeah. So 2 questions, I'm not sure if this was intentional. If you scroll up, you'll see plot 1 and plot 3, or excuse me, x1, x3 are the same. I don't know if that was intentional.
Yeah, that's right. But it's still randomly generated values.
Okay, I see
So
that.
our unit is randomly drawn values.
Okay, and then maybe you could explain the y multi.
Yes.
Just what is the actual logic behind it? Why are we multiplying, or why in this case we're multiplying x2 times 2?
So this is just a made-up function, right? So we are trying to artificially generate data. So you may have in your data set some explanatory variables and a response variable, right? And so the idea is the response variable is being influenced in some way and is related to your explanatory variables. And you are trying to extract that relationship through regression. In this case, we generate that artificially, and I'm just making this up and saying that I know for a fact that my response variable is a function of x1 and x2. Okay. Yes.
Sorry if everybody knows this already, but when you mentioned the relationship, how to have the intuition for the degrees of freedom that are lost, you said, what was the verb? When the data covers the parameters, or the data fits the parameters?
Yeah.
Which was it?
So degrees of freedom, there's a strict definition for degrees of freedom, which is the number of data points minus the number of parameters. So in this case, our degrees of freedom, we have 100 points of data, and we have 4 parameters. So the degrees of freedom should be, oh yeah, same thing as last time. There's also the intercept, which they consider as one of the one of the parameters. So it's 100 points minus 4 minus 1. So you have 95.
Since
Right. Okay, any other questions? Yes.
Can you talk about the reason why R squared value is 99?
Okay. So the question is, why is the R squared value 99%?
Yeah, or what does that imply?
Yeah, I mean, that's just an artifact of the way that I've kind of set it up. It so happens that in this case, you can see that the amount of variation in the y is not that large, right? And so when I draw a line through here, the line explains the vast majority of the variation in y. In fact, combined with the fact that there's an additional amount of variation you're not seeing here that's captured by x1, the combination of those two ends up getting most of the variation in y. And I think that has to do with the fact that the size of these guys compared to the size of the error, which is the only thing that's really going to deviate you from having like a perfect R squared. Since it's very large relative to the error, then in this case the R squared value ends up being very high. Yeah, but it's artificial, right? It doesn't, it's just a function of how I've set up this problem. Yeah. Okay, anything else?
So right now the function is just based off x1, x2, but we're creating a linear model as if x3 and x4 are also like possibly a part of it.
Yeah. So that's the thing, right? So when you are working with real world data, you're gonna have x1, x2, x3, x4, and you don't get to know like we know in this case that y is just a function of x1 and x2. You have to be like, well, I don't actually know, so I'm gonna test all of them, right? And if you have something really convenient that's all laid out nicely like this, you're actually gonna find out that the linear regression will be able to tell you, hey, like this is just a function of x1 and x2, but not x3 and x4, and that actually agrees with what we're doing. But in the real world, we won't have that relationship. Yeah. Does that make sense? Anyone else? Any questions? Yeah.
So that's how you find correlation. It may be that x2 is capturing the effect of the other one, that those two are very correlated.
So actually, so importantly, in this case, x2 has not like swamped the effect of x1. And in fact, right, you can see in cases where that would happen, you wouldn't necessarily get like both as being statistically significant. Okay. Great. Few more things for today. Nope, apparently I'm not allowed to scroll any farther. That's fine. We'll move over to here. Okay. So ordinary least squares regression, where we're doing a linear regression, means that, oh, I haven't, sorry, switched back over to the notes. 1 second. Means that I assume the relationship between my x and my y is linear, and I've been saying this a couple times, but the more accurate way of saying it is actually that it is linear in parameters. So that means that if I were to do something like this, if you have a data set that isn't linear, okay, so x and y, because linear regression is so well known, so foundational, and it's very easy to use and easy to interpret, one of the things that you can do to still be able to fit a linear regression to this, right, is that as long as you transform the data to look linear, you're still okay. And so one of the really common things, right, if you have literally any data that looks like this, any exponential data, right, of which there is lots of examples of exponential growth in the natural world, I can linearize it and still run the regression. And so you would end up doing something like this. So y, and then this would be the log of x. And the data would end up looking linear again. And then you, so instead of doing this, you could do that. Okay? So taking the log, and when I say log, we typically refer to this as natural log and not base 10, but I guess technically you could. That is a very common transformation to do because of the prevalence of data that looks exponential. And you see this a lot in like econometrics, when you're dealing with real world data, and that transformation conveniently allows for certain ways of interpretation, convenient ways of interpretation. So I'm gonna go through some of those right now, just to kind of introduce this into your toolkit about how you would think about and deal with data that would be logged. Okay, so what we're talking about now is interpreting log x, and so this is log is natural log, not base 10. Okay, so there's a couple different combinations that we can do. So the one that we are familiar with at this point, we call this level. So this is y is equal to alpha plus beta x plus epsilon. So delta y is equal to beta delta x. So what does that mean? It means if I change x by 1, if x increases by 1, how much does y change? Anyone? You should know this. It's just right there in the equation. Beta, yes, thank you. So x goes up by 1, then y increases by beta. Great. So the next one we have is log level. So this is ln of y is equal to alpha plus beta x plus epsilon. So the interpretation of this looks something like this. You do a percent change in y is equal to 100 beta delta x. So if x goes up by 1, the way you would interpret this is that y increases by 100 times beta percent. Okay? So whereas in the level, x goes up by 1, y goes up by beta. Now, x goes up by 1, y goes up by beta percent. That is how you commonly would interpret a log level. So who's seen this before in like an econometrics class? No? Okay. A little surprised. Yeah, so this is like a common shortcut that's like taught in econometrics classes. But the word of caution that I would provide, that I would kind of point to for this is, does anyone know why this happens? Why you can interpret it this way? Does anyone have any idea? Yeah, so this interpretation is only works for marginal changes. Okay, so only works for marginal changes. And the reasoning for this is ln of 1.01 is approximately equal to 0.00995, or about 0.01. Okay? So, think about what's happening here. So ln y, so if you have a marginal change in x, right, every unit that corresponds in the natural log scale for a 1% change corresponds to a 1 unit change in your x. And so that relationship lets you do this simplified interpretation. So x goes up by 1, y goes up by beta percent. But again, that only holds if you're doing small steps. Okay. I feel like I see a lot of confused looks out there, so if anyone is uncertain about this, now's your chance to have me clarify.
I think it'll be explained through the example.
Yeah, okay. Yes, we will do an example of this in a bit. Next up, level log. So this is the reverse. Y is equal to alpha plus beta ln x plus epsilon. So delta y is equal to beta over 100% delta x, which is as x goes up by 1%, y goes up by beta over 100. Okay, same intuition here. You can kind of work out the math for this, but the interpretation is like so. And lastly, log log ln of y is equal to alpha plus beta ln of x plus epsilon. So this would be a percent delta y is equal to beta percent delta x. So as x goes up by 1%, y goes up by beta percent. Okay, so these are just some quick and dirty shortcuts for anytime something is linearized by taking a log. When we interpret the coefficients, right, as a slope, we can actually interpret changes based on that like exponential change in these like percentage values. Okay, and so just keep in mind these shortcuts, and I will show an example of this in a second. Although we're actually gonna combine the example with one more topic before I show you guys the practical example. Okay, it'll be combined with something else. So the last kind of layer that we're gonna build into our foundation of linear regression for today are dummy and categorical variables, and I should actually say dummy and categorical variables in the explanatory set. When you do that for response variables, we're going to get into a whole new discussion. Okay, and that'll come in like 2 weeks. So dummy and categorical explanatory variables. Okay, so a dummy is a variable with only 1 or 0 to indicate the outcome. Okay. Can anyone give me an example of a dummy variable? What is a variable that only has 2 outcomes?
Flip of a coin.
Flipping a coin, yes, great. And so there's 2 outcomes, and so I might denote 1 as one outcome and 0 as another outcome. So 1 might be heads and 0 might be tails. Okay, but a dummy variable is actually a pretty common, pretty powerful type of variable that can describe many things, right? So it could describe, okay, a dummy variable for who came to class today. Everyone in here gets a 1. Everyone who's not here gets a 0, right? We could write everyone's name who was enrolled and put 1s and 0s next to people's names. Okay, that could be an example of a dummy variable. And this is actually a special case of the more generic version of this variable, which is a categorical variable. Okay, and so this is a variable that can take a number of discrete values besides just 1 or 0. Okay? So what's a different example of this? Your education level, right? You graduate high school, you graduate college, you got a graduate degree, right? So these are a variety of different outcomes that are discrete values and not continuous, right? And there's more than 2. Although categorical doesn't have to be more than 2, but in the case where it is 2, we call that a dummy variable, and that is the specific case of the more generic categorical variable. Okay, so the last one that I'll talk about is an interaction variable. So this is 3 or more variables whose influence is not additive. Okay, I think this definition's a little bit wonky. Don't worry about the strict definition. Let's quickly examine a example of this. So if I have, let's say, a data table that looks like this, came to class, and this might be x1, and this is, I don't know, wearing a watch. Okay, and this might be x2. So we might have student 1, student 2, student 3, 4, 5, 6, and so on and so forth. And some of the students came to class, so 1, 1, 0, 1, 1, 0, 0, okay? And then some of the students are wearing a watch, so 0, 1, 0, 0, 1, 1, 1. So we have 2 examples of categorical variables. And so you may have some kind of thing that looks like this, beta 1 x1 plus beta 2 x2. But suppose we wanted to extract an effect that is determined by the combination of both people who came to class but were also wearing watches. Okay, so that is what the interaction variable is describing. That would be saying beta 3 x1 x2. So maybe this would be like, I'd be looking at like, oh, did they come on time? Did a student come to class on time, right? And I want to examine whether or not there is some influence of having come to class and also of wearing a watch, right? And so your x3 would be the interaction variable. So this is my interaction variable, which would be equal to x1 times x2. And so you would have 0, 1, 0, 0, 1, 0, 0 when you multiply these things across. Okay? So interaction variables here, you simply multiply the variables together and include them into the regression. And you can either do that as a post process or actually you can input it as an interaction directly in the regression. Okay, questions about dummies, categoricals, or interaction variables? Okay. One second. I need to make sure this thing is in here. So we're actually going to load a data set. So you guys aren't going to, actually, I'll put it on Canvas right now. Oh, there we go again. Sorry. Should just bring some tape next time. So I'm just gonna upload this into Canvas right now, so that if you guys want, you can follow along. One moment. Sorry, I did not do this before, but if you go into the lecture files, in lecture 5, I am uploading a file called wages, and you'll want to put that in the same directory that you are working in. So hopefully from the homework, you guys will be somewhat familiar with this. Right here. So what we're going to do is we will look at a example with a wages data set. So the way that I load in this data looks something like this. So it is a CSV data set. If you don't want to follow along typing, that's fine. You can just watch up here. I've loaded that data set in, and let's take a look at it. Actually, let me do a summary of it first so we can kind of see what this looks like, as well as a structure, str wages. Okay, so here, this data set contains 6 variables: earnings, height, sex, race, education, and age. Okay? And I can do a summary of wages, and you can see that it looks something like this. Okay. People's earnings, people's height, their gender, their race, education is years of education, and age is how old they are. All right. So what we're going to do here is let's run a regression, progressing earnings on education, age, and gender. Data equals wages. So when I run this regression, okay, so when we run regressions with dummy and categorical variables, things get a little bit different. Okay? So who wants to help me do a little bit of interpretation here? Anyone? I need a volunteer. Yes. Let's do education and age. What is this coefficient estimate telling us?
The effect size of education.
Yeah, so it's kind of, right, so we've been doing these examples with generic x, y values, and we've been describing changes in x and outcomes in y as like a slope, right? And so this education, you said the effect of education, so this is kind of like a slope still. So what does that mean? Can you help me out here?
I mean, I was looking at if you look at the education, like the variables, it's like numerical, so then like as you go up in 1 unit of education, you'll add that
Yeah.
amount to the wage.
Yeah, exactly. So the interpretation is in the data as we see it, we observe, right, that on average, as someone increases their education by 1 year, if you have 1 more year of education, we see a corresponding increase in earnings of $4,469 on average. Okay, so each year of education increases earnings by this amount, and that is. So the nice thing with the linear regression is it's like isolated this effect, holding all else equal. And so if 2 people were of the same age, but 1 person had 1 more year of education, on average, their earnings we would expect to be this much higher. We do control for age, which means what? So people who are older make more or less money. More. Great. And the amount that they make per year that they are older is $280 on average. Okay? All right. What is this variable? So we have this factor sex male. Okay. So recall back to lecture 2 when we talked about data types. Right, factors are ways that we can turn essentially a qualitative variable into something quantitative. So there's some kind of value that's differentiating, male and female, which is why we're able to run this regression. You can think of it as the behind the scenes, the model has assigned like 1s to males, or in this case, it would have assigned 0s to females and 1 to males, just as in alphabetical order, so F comes before M, so it's by default 0. Okay, so education and age, I described both of these things as slopes, right? As you change in education, as you change in age, but whether you are female or male isn't really like a continuous variable. It's just a categorical or dummy variable, right? And so in this case, it is saying if you are male, you would on average make, the earnings in this data set show that you make $21,000 more on average, okay? Does everyone see that? So, this is actually more like an intercept than like a slope, okay? And in fact, if I were to look at a model, let's do this really quick. Okay, here we go. Okay. So let's pretend for just a second that I didn't have age and that we only had education in the model, right? Kind of what you would be looking at is this: education, wage. You would have a line like this, right? And so as you have more years of education, wages increase. This is our intercept. And in fact, we would have a second line that looks like this. And so this would be intercept plus plus the coefficients on male. Right, so they are shifted up by 21,000, but the slope of the education term didn't actually change. Okay? And so if this is describing, if this curve that I'm drawing is describing the male wage, then what would be describing the female wage? Anyone?
A negative coefficient?
Yeah, so it would be this other line, right? And so in here, you'll note that I don't have a separate coefficient here that says factor sex female, because that effect is like baked into the intersect. Okay, so anytime you have a dummy variable or a categorical variable, when you run the regression, one of those levels in your dummy or categorical variable will get left out, and the thing that's left out is being described by this intersect. Okay? So, I know that it's not physically possible, but if you are 0 years of age and you have no education and you are a female, what would the model tell you would be your wage? Yeah, negative $48,000. If you are 0 years old and you have no education and you are a male, what would this model say your wage would be?
Minus 27.
Yeah, so it would be negative 48,000 plus 21,000. Right, and so that would be 27,000, negative 27,000. Okay. Okay. So we are not quite done with this portion for today. For this example, we're going to do a little bit more, but actually we're going to end for today. This is a good stopping point, and then we're going to pick up where we left off on Wednesday. Okay? So yeah, thanks everyone, and just a reminder, remember to get your homeworks in by the end of the day on